In this SimScale podcast, we will speak to David McCall about his experience as a mechanical engineer and ultimately how the design process is changing across many industries and for many applications, from bowling alleys to RF testing equipment.
My name is David McCall. I have a little bit scary, but I have almost 20 years of experience in mechanical design, everything from industrial robots that do floor scrubbing to bowling pin spotters to thermal housings for military and police type situations.
Wow.
So I don't know if we want to go any more detail than that, but
What prompted the floor scrubbing robots? That's awesome.
well, actually, that was my job. I got as an intern while I was still in school. They had it was a spin-off from I can't remember the name of the company, Kent or something like that. The companies that do the manual push behind floor scrubber, you see in hospitals and schools and grocery stores and that kind of stuff, the big ones. And they had bought the intellectual property of the company, and there was a stack of AutoCAD drawings about 3 inches high. And when I was an intern, they said, "Here, take this stack of drawings and this CD," because they had gotten all the soft copies too. But the CD, take this hard copy and compare the hard copy with the file that's on the CD and make a three-dimensional AutoCAD SolidWorks drawing out of it. So that was my job as a summer intern, and that morphed into a full-time job doing the same thing. And then when I graduated, they wanted to hire me, but they were running into financial difficulties. So I went off and did something else for 9 months, but then they hired me back as a full-time engineer to basically redesign it, because it was kind of a science experiment that they were trying to make as an actual product.
Right.
But we kind of took that and made it easier to produce and redesigned it for assembly and stuff like that, and took everything from powder coated stainless steel down to aluminum, because it was battery powered. So it had this giant, basically four. They weren't car batteries, but they were designed for like boats. The trawling motors, the deep cycle lead acid batteries. But there was 4 of them in a series, and so they were probably 100 kilos for the batteries.
Wow.
Inside this thing. So we're trying to reduce the overall weight of the thing. Obviously the chassis is not the significant weight when you got 100 liters of water and 100 kilos of batteries on board. But anything you can do to reduce the weight is going to increase your battery efficiency. So that was one of the things we did, was made it aluminum versus steel. And
Wow. So would you say that that's like, I mean, probably not, but I don't know. Would you say that's like your favorite project you worked on, or like, can you name a different one?
No, I don't think that's my favorite. I mean, that was definitely the first project I worked on. I think the favorite one was probably when I was working at the bowling. I worked at Cube Game F, which is old AMF bowling, which does pin spotters. We used to say that you could give AMF a warehouse, and in about 6 months we could give you everything but the kitchen that went into a bowling alley. We did floors, we did the alleys, we did the pin machines, we did the shoes and balls and everything like that. But one of the projects I worked on was they were designing a more reliable, lower cost machine that was on strings. So there's 2 different types of machines. One called free fall, which is the traditional bullet. You go into a bowling alley and the pins are just flying around. But they had one that's a string machine, so it's easier. There's like a quarter of the parts, but they're cheaper and more reliable, and they just they're designed for if you got a bar or a restaurant, or maybe I don't know if you have them in Europe, but we have a chain called Chuck E. Cheese, and it's basically a pizza chain with it's an arcade that happens to sell pizza. But we had a lot of those there, where there's you've got a 18-year-old kid who's basically in charge of maintaining the machine, so you have to have a really cheap and easy machine to maintain. And we designed a a system that was the pins were on strings, and it was flexible enough that you could actually either use the full size pins. And if I was in my office, I could show you one, but it was a full size pin, or you could replace the pins and put into a full arcade system. It was flexible enough they would do both. So we had ones that were full size lanes, and then we had ones that were coin operated, called a Highway 66 machine.
I remember going to Chuck E. Cheese as a kid.
Oh yeah, okay. Well, no, I don't know if they ever had them, because this is probably 2005, 2006 when that machine came out.
Okay.
So yeah, probably a little bit after your time, but
a little bit after, yeah.
Yeah.
Cool. Well, that's really awesome. What motivated you to initially kind of get involved or like become an engineer, I guess?
I probably Legos.
Okay.
I think because I like the idea, and I got into engineering, and I got into design engineering in particular, because if you look at if you do a Google search for mechanical engineers, there's basically two different types of mechanical engineers. There's the guys that do the structural engineers, that build buildings, and they put in, air conditioning and plumbing and stuff like that into buildings. And that's one type of mechanical engineer. The other type of mechanical engineer basically builds products, like the bed behind you, or the dresser, and kind of builds that kind of stuff. So products and commercial products and stuff like that. And I went that way because I like the idea of being able to take a thought either in my head or in a group's head and make the pixels on the screen in CAD, and then take that concept from the CAD all the way to physically having the product in my hand, either 3D printed or machined or whatever it is, and then being able to take that concept and being able to produce them.
Wow.
So I haven't really worked on commercial products. So I haven't really worked in the high volume stuff, but I definitely enjoyed the idea of being able to take, this is a concept in my head, and this is a concept on CAD, and being able to hold it and build it and play with it. And that's kind of like what you do with Legos. You got this giant pile of bricks, and you can build whatever you want with them. And it's the same sort of thing. Instead of dealing with, plastic blocks, you're dealing with screws and bolts and bent metal and machine metal and stuff like that. So that's
makes sense.
Are you still playing with Legos though?
Oh yeah, no. Here's this has been my desk here.
Oh, that's cool, because I do as well.
Here's, I don't know if you can see that, but here's my.
Yeah. Awesome.
Is it? What is it?
That was my birthday present this year for my kids. So yeah.
Awesome.
Oh yeah, no.
Well, I wish I had Legos now. But more about like the product design process, I guess. We have a quote from you from engineering.com, where you said it's a lot more, like in terms of working with SimScale, it's like a lot more cost effective as opposed to getting a seat and having it sit there for 3 to 4 months. So can you tell us a little bit about like maybe your experience with different design processes that you've come across, and like if you've had design processes that were like really slow in the past? I'm assuming yes, based on this quote, but.
Well, yeah, because so when I started, back in the Stone Age, back in the late 90s, early 2000s, it was a lot of, you would design something in the CAD, and then you had to take that file and you had to send it off to a machine shop, and you would have to get the parts bent or machined or something like that, and then 2 or 3 weeks later you would get the parts in your hand, and you were pretty confident that they would fit because you would check hole alignments and the 3-dimensionals. But that was even a light year ahead of what we had 3 or 4 years before that. So when I started my career, SolidWorks and that kind of stuff had just come out, and 3-dimensional was the bleeding edge, and people were dealing with AutoCAD. So if you're familiar with AutoCAD, it's just a line drawing, and you can't really do anything with it. And you would just have to make sure you did the math right and make sure the holes would line up on the 2 pieces. Well, it didn't always work that way. I mean, I worked with a guy whose parents were building a addition onto their house. They had a 1-story house, and they were adding a 2nd story to it. And they got about a quarter of the way done roughing out the structure and realized that they were off by 6 inches. so nothing lined up, and they had to tear the whole thing down and start over. And that happened to me before. So it's like, when I started my career, it was like you were kind of hoping that you had everything aligned, and then you had the 3 dimensions, and you could assume that in the first pass the holes would line up. But now with simulation and 3D printing and stuff like that, the first step of the process is to make it out of plastic, regardless of where you're going with the metal. You could have a metal part, but you're going to 3D print it, because that's going to cost you 4 hours on a 3D printer. And you can buy a 3D printer for $500 or $600, so it would be big enough to do anything. So you can print it, and the material properties aren't going to be the same, but you can be pretty confident that the parts are going to fit. And you can show the sales guys, and you can say, well, here's a plastic representation of what the part is actually going to look like when I get the metal parts in. Is that okay? So you can save a lot of steps, because literally you can do that overnight. You can leave at 5 p.m. and say, in the morning I'll pick up my print, glue it together, and show it to the sales guys, instead of having to go and say, wait 2 or 3 weeks. And it's the same sort of thing with simulation. You can take the ideas where I'm building a metal box. And if you give me a second, I'll show you one.
Showing us everything.
Sorry, jumping away here.
We've seen Legos, we've seen boxes. This is exciting.
Yeah, so this is a full IP66 rated, which means if you're not familiar with the IP standards, it means I could drop it in a puddle and it would shake it off. The next step is IP67, which means you can use it underwater. We can't use it underwater because it has got connectors here, and it's got a door here. So if you open the door, obviously we'd flood the unit. But the idea is that before I would have to take this unit and attach thermocouples to the outside or thermocouples to the inside. But with the simulation packages like SimScale, I can take this design, and in the CAD, I can kind of be, 80, 90% confident that the heat is going to go where I want it to go. And there's a previous generation of this box that had issues where it would get so hot that we actually scorched the outline of the box into a conference room table, because it just got hot that it melted the plastic a little bit on the conference room table. So forever, that table had a little rectangle on it that we said that's where the unit sat too long on the. And right after that, we put rubber feet on it just to make sure that the box wouldn't touch the table. But yeah, so that's kind of where we go. So the idea is that you can get the design, 80, 90% of where you want it to be without ever having to physically, order metal. And that's the cool part of working now, because you can make the parts out of plastic, have everybody sign off on it, and you've only sunk a couple $100 worth of material versus this box here. The prototypes probably cost $2,500. So you can see the improvement in cost. Where instead of when I started my career, you'd have a box like this, and you would get close and you would buy it, and if you missed it, you just spent $2,500 and you had to scrap all that. Whereas now you can say, you're only burning labor costs, you're not burning material costs at that point.
So we obviously talked a lot about this thing called prototyping now. Do you think prototypes in the future will become even less? Because even in the aerospace industry, they discuss a lot about, okay, do we still need prototypes in the future? How do you think about that? Do you still think it's needed, although we have simulation tools available?
Well, I think you're always going to want prototypes, because you're always going to have sales guys that are like, or customers that aren't going to want to see just a picture. They're going to want to be able to feel it and touch it and play with it. But I think the way I kind of think about it is that you're adding more steps to the prototyping process. So like the way I described it, say, it used to be that the first step of prototyping was to order metal, right? Well, now in 3 dimensions, the first step is kind of, you've checked it in the CAD. So the first prototype is your 3-dimensional model that is basically complete. So, you've got screws and bolts and everything like that. Mm-hmm. All the parts are modeled in the 3-dimensional space. So that's the first round prototype. The second round prototype would be a 3D printed piece, mm-hmm. where you have it, fit and the fit would be equivalent, but it's obviously not the same material. So you can't put the computer in it and fire it up because it's plastic. It's not gonna, it's gonna melt, and the computer's gonna overheat because it's not cooling. But it's the same shape and size of what you're actually building, right? And then the third step, so now instead of one step going straight from CAD to metal, you've got not 3 steps. The third step being physically ordering metal. So you're never going to get, the problem with it, the simulation tools, yeah, they're good, but you're kind of, especially on new products, if you got a product that you've already existing and you're just kind of improving it, you're pretty confident that your data going into your simulation is going to be good, because you can say, here's what the physical product looks like. But the problem is with a new product that you've never seen before, you got a different computer or a different card in it, you're kind of using an assumption. So, you can kind of use some of your, professional judgment to say, I know what it's going to look like, but you kind of have to use the physical prototypes to check the assumptions in the CAD and the simulation. So that you're never really going to get out of that step, I think, unfortunately, because it's like, right. Simulation is good, but if your assumptions going in are wrong, you're going to get the wrong data out. So you kind of have to, the step of the prototype is to say, here's what the simulation picture told me. I run the prototype on the bench top with the thermocouples to check the data coming out of the simulation and say, okay, well, this was close enough, the temperatures are within 5 or 10 degrees, or depending on what your thing is, or you say, it's better than that or worse than that or something like that. So you kind of just check the assumptions, and then what lets you do is you say, okay, the next time I knew my assumptions were right, or I knew my assumptions were wrong, and I can kind of correct my assumptions. So it kind of helps you depending on how close your new product is with your old product. And that's always the problem.
That's cool that you said that, because it's quite hard to capture the reality, because it's so highly nonlinear and there's so many parameters involved. And there's this famous quote from George E.P. Box, who is a British statistician, maybe you know that one, who said that all models are wrong, but some are useful. And I think that it's nail on the head.
Yeah. Oh, yeah, for sure. Yeah. In disease and thermal simulation, that's very true. And it's just a question of, can you use your judgment or your experience to say, okay, is this model close enough that I can move on to the next step, or do I have to say, okay, I don't know enough to? And I've done that before, where you kind of said, maybe the overall box is too complex to have, and I got too many assumptions going in. Well, I can take smaller sections of it. Because one of the things I did on the box that I showed you, where before, in previous generations, it's got a computer on top. It's a single board computer. And in previous generations, we literally heat synced that computer board to the chassis, right? Mm-hmm. Well, what we discovered was there was a hot spot there. Obviously, you can just think about it. You're putting a CPU that's got 65 watts onto the heatsink. Well, one of the things we did in this generation was we decoupled the computer from the chassis. So internally, and if I could show you that, there's actually a block inside the box that is directly connected to the computer. But instead of that box being directly connected to the chassis, that box is connected to the chassis via heat pipes. Mm. The advantage of doing that is that I can kind of take the heat where I want it to and spread it out. So instead of being localized where the processor is, I can spread it out over the entire surface area. Well, we'd never done anything like that before. So one of the things I did in the simulation was kind of just simulated that with just blocks. So I had a block over the CPU that I just put a heat source into that block, and then simulated the heat pipes into a giant rectangle, and just kind of without any fins or anything like that, and just kind of said, okay, well, how is this heat going to spread out into this, so one rectangle to another, assuming heat pipes were embedded in both, and I could say, well, I still got a hot spot here, so I want to tweak that heat pipe so that it's kind of spreading it out more evenly. So instead of having the chassis being red in this one spot, I wanted to get the whole thing yellow, so it's more evenly spread out. So that, because the problem when you've got no fans or none of that, the more even you can get the heat, the better you're going to radiate into the environment. It's just, unfortunately, physics, you can't change physics. You have to deal with physical laws the way they are.
You can't change them? What? News to me.
No, they try, but.
Well, jumping back a little bit to, we're talking about simulation. Could you kind of tell me, like, in your professional career, your first experience with like CFD or thermal simulation?
Well, my first experience with simulation was actually CFD. Back at the bowling company. We had to do, one of the requirements was that it had, because bowling alleys, the owners of bowling alleys hold on to their machines for a long period of time. Like, we had machines that were built in the 60s, and they were still using them in bowling alleys in the mid 2000s.
Wow.
So these are 40-year-old machines. So they're like cars. People hold on to them for a long time. So one of the things is, if we were going to switch a supplier, or we're going to do a design improvement, the piece that we're going to change had to be able to. It would depend on the part, but it had to be roughly 100,000 cycles. And a cycle depended on where it was in the machine, but for the most part, it had to be being able to be hit with a 16-pound bowling ball for 100,000 cycles. So that tells you how many impacts, 100,000 impacts at 16 pounds. And it was assuming a 16-pound bowling ball running at 20 miles an hour. So we're assuming worst case scenario of a professional bowler using a 16-pound bowling ball, obviously 16 pounds being the heaviest ball available, based on the rule of bowling, if you didn't know bowling. But anyway, so it was 100,000 cycles. Well, the problem there is that, you're tweaking a product. You wanted to make sure that before you even pulled the trigger on ordering prototypes, you wanted to make sure you were close. So one of the things we did was a stress analysis on the part in CFD to assume that if I take this material out, it's not going to make it brittle or something like that. And so then you would simulate that, and then you would make sure that it passed that, and then you would obviously buy the prototypes, and then you take it out to the lab. And that was an interesting experience, because that bowling alley, the bowling ball testing facility was interesting, because we had you go out there and you always had to wear ear protection, because we're always testing. One of the things we're always testing is the lane material. And after but bowling alleys. But if you look at a bowling alley lane, unless you got a really old one where it's actually wood, for the most part, bowling alleys are actually the same material that's on your kitchen counter, the laminate.
Oh, okay. But
instead of being 3 millimeters thick, which is what the standard is, maybe slightly even thinner than that, depending on how cheap you wanted to get. They were actually 3/8 of an inch, which is roughly 10 millimeters thick. So much thicker. But we're always having problems with them. So one of the machines we had constantly running was dropping a bowling ball from 10 feet, so onto a lane. So and one was basically every 10 seconds, it would drop a bowling ball onto a lane. So you hear this constant thunk, thunk, thunk. So you had to wear ear protection. And that was the same sort of thing. We're just, we had ball throwers that were like, have you ever seen the pitching machines? I don't know if you're familiar with those, but they have them for footballs and baseballs and stuff like that. They're basically two tires that are spinning. And we had one of those for a bowling ball that would launch a bowling ball. That was
what's like the lubricant stuff that they have on bowling alley, like in the lanes?
It's mineral oil for the most part.
Oh, okay. Didn't know. Yeah. Learn something new every day.
Yeah. Well, it's because it's the problem was this: you're in a wood environment, so if there's any sort of water-based thing, it would get into the wood, and the wood would start rotting. So they had to use mineral oil because it would just kind of be absorbed into the wood, and it wouldn't hurt the wood.
So now that you have all this background knowledge on bowling alleys, are you like the best bowler in your area?
Yeah,
No?
I'm terrible.
Oh.
Yeah, no, unfortunately. It's like I used to say that my bowling score and my golf score were both about the same, both about 100.
Oh.
Neither one of which are good, but but yeah, so I wish.
Now, coming out again back to simulation, what would be your perfect workflow? Of course, we have this 3-step process, right? Where you have pre-processing, processing, and then of course the post-processing part. In each step, would you specify something, or would you change something specifically to your needs, or how would your perfect package look like for your application?
It kind of depends on where you are in the process. If I'm doing a section of the model, I think it's pretty good the way it is. The issue is that, I always like to do a final full up simulation where I've got all the parts designed. I'm gonna, right before I, buy the physical parts to build the prototypes, I want to do as close as I can simulation of the entire assembly, with all the components in the entire thermal chain. And that's always tended to be the kind of the choke point I've seen, where it's kind of like when you've got 10, 15 thermal sources, in this part here, if you actually see it, there's actually a seam right here.
Yeah.
Picture. But so there's a radio on this half, and then the computer is on this half. Well, there's actually a connection. There has to be a connection in between the two to get the heat off of this half onto this half, because it normally sits like this. So this side obviously is going to be sitting on a desktop. Well, it's not going to cool very well. So in order to get this half cool, I have to get the heat up here. Well, that became a problem. One of the problems I had was figuring a way to, in the simulation, connect these two with heat pipes. So that's kind of the issue, where I can very easily simulate both halves, but it's when you've kind of got almost two simulations stacked up on top of each other, really, because they're really only connection is a piece of thermal pad. So you've got
what material did you use for your heat pipes? Is it like the classical?
It's basically I used a custom material.
Okay.
I used I knew from the data sheet of the heat pipe, I knew the thermal conductivity. So I just modeled it as a tube and then put the thermal conductivity on that material. And that's always been a problem. Like, I don't think there's any package that has a proper model in their database for a heat pipe. I haven't found one that has one here's a heat pipe, and you can just pull down and say heat pipe. But you just you just know that going in, and you can say, okay, well, I'm gonna create and you just kind of pull the data sheet off, and you say, okay, well, when I create a simulation, here's the data that I'm going to use, and you kind of can make it so that you know that each time going in, you're going to use the same thermal properties, and you can kind of keep it repeatable.
Right. I guess that kind of leads into our next question, really. Like, so I guess where would you predict, or like where could you see computer-aided engineering tools going in the future? I mean, I guess holding heat pipe material information, but other than that.
Well, I think you can kind of see the whole industry going cloud-based, I think. Just because, with the more information you add to a simulation, the more CPU processing power you need. So it's like a trade-off between, okay, do I buy a 16 core processor that's on my desktop to be able to run the occasional simulation? Because the problem I ran is that, and one of the things I liked about the SimScale package was that you can rent the whole thing. or if you've got a traditional simulation package that you purchase a license to, right? Well, you've bought the license up front, and you kind of, you've spent $15,000 on the license. Well, then you use it every 3 or 4 months, because it's got the way I've dealt with it. Our team isn't huge. We only had 4 mechanical engineers, but even then, you're not going to simulate every day, because you're not going to need to. There's going to be phases of the project where, you're going to be for this couple of week period, you're going to be simulating every day, because you're kind of, iterating the design, and you're kind of, well, this part is okay, so I'll move on to this section of the model, and I'll simulate that and kind of improve that. And then you can go, okay, well, I've got all the piece parts now, let me simulate the whole, right? Well, that could be, like I said, 2 or 3 weeks, but then you're finished that section of the product and you moved on to ordering prototypes. Well, you're not going to simulate anything at that stage, because you kind of put the design into sleep mode while you where you're building the prototypes. And then you can go in and say, well, I've got the thermal data based on the prototypes. Then you kind of go back into the simulation and you say, okay, well, how do they match up? Is the simulation saying it's here, and then the reality is saying it here, and then you got to analyze it and say, okay, well, where's the disconnect? What about real world is telling me that is giving me this temperature, but then what did I do wrong in the simulation to say, okay, it's up here, or vice versa? It could be that that has kind of happened before, where you've got the simulation saying it's going to be at 30, well, the prototype saying it's 45. Well, oh crap! Now what did I do wrong? And that kind of stuff is, I like the cloud-based system, because you can go in and say, okay, well, I'm gonna buy so many hours. Well, I don't have to feel pressured to use those hours, because I've got a seat sitting somewhere and just burning capital. But I can, and the other advantage of it is I can do other things with my machine, because one of the problems with simulation is it locks up your machine, and you can barely check your email on the machine, because it's taking 99% of the processing power and 99% of the RAM, and you can now I can't even talk on Slack or talk on email, because my machine is locked up. And it's nice to be able to put it in a CAD window and go in a browser window and close the window and come back after lunch, or check it on your phone or whatever it is. And I think the whole industry is going in that direction, even with simulation and the CAD. It seems like the whole industry is kind of going in that direction. Now, there obviously are still the issues with, the older leadership doesn't necessarily see the security in the browser thing. So it's like, okay, well, you're sending my IP off into the cloud somewhere, and it's like, yeah, I guess so. And Onshape and those guys are going to have that same problem too. Sorry, Mike. One of the advantages of this whole COVID thing is the VPN systems have gotten a whole lot better. A whole lot more.
Very true.
It might be the point where you could VPN into your cloud machine, with your cloud-based simulation provider, and then you've got a secure tunnel, and you can pass secure data or something like that. I don't know. Not a software.
Yeah, that's excellent. So you heard it from David now. Cloud-based ecosystems are the future. So with all of your experience, we want to wrap things up. Do you have any tips for people getting into the CAE market or in simulation in general? What would you recommend? Just simulate and learn from your mistakes, or what would be your advice?
Yeah, I think that's kind of the best way to do it. That's the way I've kind of dealt with it. Is just kind of like, and also is to don't bite off the whole model at a time. So I definitely learned the hard way when I first went at the tool, and I hadn't really used the simulation package very well. I went in with the assumption that I could take the entire built-up model and just simulate it. And that was definitely the wrong way to go. I think the idea is that you should take a section of the model, even it being, just here's the interface of the CPU to the chassis, simulate that, and just get used to using that, and then build up on like that, so that you have all the building blocks to get to the whole. And then once you've got the building blocks, then you can say, okay, I'm going to combine all these blocks into a full simulation of the entire product, and go that way. So it's like, you know, because I remember it, and this isn't against SimScale. This is me using the tool the wrong way. I think when I first signed on to SimScale, I used it. I probably stared at it for a week, and just like getting wrong data out. I'm simulating, and I'm like, the chassis is at 100 degrees C. There's no way. It's not impossible. I've got a physical prototype in front of me, and the physical prototype's running at 45. Like, what is the difference? What am I doing wrong here? And I realized that I put the heat onto the whole thing instead of one square, and I figured it out. It's like, oh yeah, okay. But yeah, it's just, you can't go in it and say, you know, here's my product, let me thermocouple. The way I thought about it was, here's my product, let me thermocouple it, right? But simulation kind of wants to be done the other way, where you have sections and you kind of say, okay, so instead of here's my whole product with 10 thermocouples, I've isolated down to one thermocouple and play with that, make sure I know that one's right, and then go on to the next one. So you build like I said, the blocks, and you build that up to a whole.
That's excellent.
My hard-won knowledge. So.
Yeah, but it's also life advice, right?
Yeah.
Also life advice, like to divide and conquer. It's like in simulation, but also in life.
Yeah, that's true. Yeah.
Yeah.
You gotta build one step onto the other.
Yeah. Cool. Would like to thank you so much, by the way, David, for being on our show and having the time to join us.
I think you should actually hold up like the Lego one more time.
Yeah, here on this.
That will be used for our thumbnail.
There's our thumbnail. From Legos to thermodynamics.
Yeah, there you go.
All right. Well, I hope you have a great rest of your day. I know it's quite early over there. So yeah, and we'll speak soon. Thank you so much again.
Right. Sounds good.
Thanks, David.
Cool. Bye. Thank you.
Bye.
Bye-bye.